So for this one, a car is being lifted into the air, 2 meters into the air by this lift, and the mass of the car is 1,400 kilograms. We want to find out how much work is done. And then let's assume that it's being lifted at a constant speed. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so when we look at the forces, the positive force applied plus the negative force of gravity, if it's going at a constant speed, acceleration is 0. So it's being lifted at 13,720 newtons over 2 meters, and we should get 27,440 newton meters or joules as it's lifted up. Now let's say that it takes 20 seconds for it to be lifted up. Go ahead and calculate the power. So throughout this tutorial, I would encourage you to get your equation sheet, and you can use that as you work through these. All right, so you should get power output of 1,372 watts work over the period of time. All right, so for this one, if you look under your equation sheet, under it says gravitational momentum, it's important to remember what each of those different equations are. And in this one here, we're looking at a change in momentum that's happening with a force over a period of time. So this is impulse. So the ball goes, hits, and bounces back. And so it's rolled towards a concrete wall at 5 meters per second. So V initial is positive 5 meters per second. And it says it bounces back at 3. So that means that, and one of the really critical things here is the signs, right? So V final is negative 3 meters per second. Now, if you forgot the negative, what that means is the ball is continuing to go forward. It blasts through the wall and then slows down to 3, which is definitely a different situation than this. So go ahead and calculate the change in momentum first, and then you can calculate the change or the force. So go ahead and pause the clip, give this a try, and when you're ready to check, you can hit play. All right, so we should get a change in momentum of negative 72 kilogram meters per second and a force of negative 116.13 newtons, the force being negative. And that should kind of make sense because the ball hits, bounces back, and we've got that there. All right, so conservation momentum. Total momentum of all objects interacting with one another remains constant regardless of the nature of the forces, right? So the total momentum before equals the total momentum after. And this is an important relationship when we're looking at problem solving. So let's go ahead and try this one here. We have a 5 kilogram projectile launcher shooting a bullet and at 350 meters per second. And what is the recoil velocity of the launcher? So you're going to want to set up M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Now in this case here, it's starting from rest, so both of those are 0. But yeah, go ahead and figure out what the projectile launcher will do. And so go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so we launch it out, and the launcher should go back at negative 14.63 meters per second, and that's going to the left. You could have called, the launcher mass 1 or mass 2, doesn't matter. And then your final answer will be based on your picture there and what you set up with the variables. All right, so let's go ahead and try this one here. We have 2 cars going on a head-on collision, and we want to find out the resultant velocity after the crash and then the change in energy. So yeah, go ahead and pause the clip and set up your variables. We'll call mass 1 the one going to the east, the other going to the west. And again, here, if it's going to the west, what is V2 initial then? Negative 25, right, meters per second. So just be careful with your signs. Go ahead and pause the clip and just go ahead and get to the resultant velocity first. We'll make sure you're good there before we do energy. All right, so we should get a final velocity of negative 8 meters per second after the cars collide. And so they're going to have the head-on collision, then they'll start going back to the left. All right, now what we want to do is look at the energy before and after. So yeah, I'll go ahead and pause the clip and calculate the energy of both cars before, both cars after, and then see what the loss is. Okay, so beforehand we should have 510,400 joules, and then afterwards we calculate both 1/2 mv squared 102. So there's a loss of 408,000 joules, a lot of joules lost, and then head-on collisions are really really bad, and so we see that energy loss here.